Hello students, Mr. Keister here again with you today. Today we are going to continue on in Unit 11.2, which involves redox reactions and electrochemistry. Today we're going to look at how to balance a redox reaction in basic solution. Let me bring up the do-nows that would have happened today. Let's see here. Sorry about that. Can't see really well. There we go. All right. So had we been in school, again, these are the do-nows that are originally for the school year, had we been in school. So for Chem 2, this would have actually been our lesson on Monday, April the 6th. Actually, today is actually the 31st of March. I'm here videoing this lesson today. But again, had we been in school, it would have been Monday, March the 6th. Our assignment is actually page 179. So before I do this lesson, I wanted to do a quick review of how to balance a redox reaction in acidic solution, which was yesterday's lesson. I feel like it'd be worth it to go over that one more time because today's procedure is very similar to that. And so I want to go over that one more time and actually do a sample problem off your homework that was due for today. One that really kind of incorporates all of the steps involved. So let me bring that assignment. Actually, let me bring the notes up first. Let's see. There we go. So here behind me now should be, this is what we went over in yesterday's lesson. So in balancing a redox reaction in acidic solution, first thing we do is divide the equation into two incomplete half reactions, one for oxidation, one for reduction. Again, we have to do that first. And the way we do that, of course, is to determine what got oxidized and what got reduced. So our basic knowledge of oxidation numbers is very, very important. So then we balance each half reaction using these steps in this exact order. First, balance everything other than hydrogen or oxygen, just like you would normally in a regular reaction using coefficients. Secondly, balance the oxygen on one side of the equation by adding the appropriate number of waters to the other side of the equation. Third, balance the hydrogen atoms on one side of the equation by adding the appropriate number of hydrogen ions to the other side. Again, we're in acidic solution. There are hydrogen ions present. Fourth, balance the charge by adding electrons to the side with the greater overall positive charge. So we're going to add electrons to the side that is more positive, all right, so that it can then bring it down to the number of, to make the charge equal, in addition to the atoms and ions being equal. If necessary, multiply each half reaction by an integer so that the number of electrons lost in one half reaction, which would be your oxidation half reaction, would equal the number of electrons gained in the other half reaction. Electrons gained, of course, would be in our reduction half reaction. Add the two half reactions together and simplify where possible, and then check to make sure your charge and atoms and ions are all balanced. So that was a little review of what we do. So what I'm going to do now is bring up yesterday's assignment, which is right here. I'm going to go to the second page, and we are going to look at the last one, number 7. All right. So going by the steps, first thing is we got to determine what got oxidized and what got reduced. So we're going to look and just follow our normal oxidation number rules that we learned a while back. So here we have arsenic as a neutral atom. Of course, its oxidation number is 0. Here we have the chloride ion. So oxygen and the chloride ion, like it is in virtually everything other than peroxide, of course. Oxygen is -2. There's 3 of them, of course. There is only one chlorine in there. So since the charge overall on the chloride ion is -1, then the charge on chlorine, when added to this -2 times 3, which is -6, would equal a -1. And so chlorine then in this particular ion has an oxidation number of +5. H3ASO3, this is actually ASO3 is the arsenate ion. That's not one you had to learn. And so based on that, this acid then would be arsenic acid. Again, I'm going to start with O. O, of course, is -2, as it is in virtually all compounds and ions. Hydrogen, when bonded to nonmetals, of course, is +1. That's an important rule to remember, too. And so based on that, so we have a -6 total off of the O's, a +3 total off the H's, which is then going to leave arsenic at a +3 oxidation number. And then HClO. Okay, well, ClO is the hypochlorite ion, so this is hypochlorous acid. Again, O is -2. Hydrogen, when bonded to nonmetals, is +1. So that is going to leave an oxidation number of +1 for chlorine. So based on that, we could see what atoms or ions got oxidized and what got reduced. Well, reduced, remember, becomes more negative. Looks like O stayed the same all the way through. It was -2. Chlorine here is +5, and over here it is +1. So it is reduced in charge, and so chlorine then is our reduced substance. Arsenic, which started out as an oxidation number of 0 and ended up as +3, became more positive, so that would be oxidized. So we're now ready to write our half reactions. So our reduction half reaction will involve chlorine. So the substances that contain chlorine would be ClO3 -1 on the left side, that's AQ, and HClO AQ on the right side. Then our oxidation half reaction then would involve arsenic. Those substances then would be AS solid on the left side and H3 ASO3AQ on the left side. So there are two half reactions. So now we're going to run through the steps, excuse me, in regards to balancing each of those half reactions. So first, we balance everything other than H or O. So in this first one, that would involve chlorine. We have one Cl on the right, one Cl on the left. It's fine. On the bottom one, we have anything other than H or O as arsenic. Here we have one AS, here we have one AS. It's fine. So now we'll move on to the next step. Balance the O's by adding water to the appropriate side. All right, so here we have 3 O's on the left. Here we have only 1 O on the right, which means we're going to need 2 more O's on the right-hand side, which means we're going to add 2 water molecules, or 2 moles of water molecules, I should say, to the right side. For down here, we have 3 O's on the right and none on the left, so we're going to add 3 waters on the left side. That takes care of the O's. Next, we're going to balance hydrogen using hydrogen ions. So, got to be careful, make sure you count them all. So here we have 1 hydrogen, and here we have 2 times 2, which is 4 more hydrogen. And so we have a total of 5. There are none on the left, so we're going to add 5 hydrogen ions on the left side. Remember, when we start off, we always kind of write the half reactions in the middle because we end up building on either side of those as we go through the process. For the bottom one, we have 6 hydrogens on the left. We have 3 on the right, which then means we are going to add 3 hydrogens to the right side. I'm going to double check my notes here. Yes. So I have 6 here, 3 here, 3 hydrogens. Lastly, we're going to balance the charge by adding electrons to the appropriate side. All right, so here we have 5 hydrogens. That's a +5. Overall, here the charge on this ion is -1, so we got +4 over there. Everything's neutral over here. All right, everything's neutral. So we're going to add electrons to the side that's more positive. That would be the left side, and we would need to add 4 electrons. Which makes sense. Keep in mind, reduction is a gain of electrons, right? Reduction is a gain of electrons. And so in a reduction half reaction, the electron should always, always, always appear on the left side of the equation. On the right side, or on the bottom half reaction, we got neutral and neutral here. We have neutral here, and we have 3 +1s over there, which is a charge of +3. So we're going to add 3 electrons to the right side to bring that into balance. And again, on an oxidation half reaction, remember in oxidation electrons are lost or released. And so in an oxidation half reaction, the electrons, again, always, always, always would be on the right side of the equation. So we've gone through all that. Next, if necessary, multiply each half reaction by an integer so that the number of electrons lost in one half reaction equals the number of electrons gained in the other. They must balance. They do not in this example. Here we have a gain of 4 electrons. Here we have a loss of 3. That is not equal, and they have to be. So we're going to multiply this top reaction by 3, and we're going to multiply this bottom one by 4. All right, least common multiple, so that our electron transfer is equal. So I'm going to change up my coefficients now. So this becomes 12, this becomes 15, that's 3, that's 3, and this becomes 6, and that takes care of the 3. Down here, I have this 3 becomes 12, that's 4, that's 4, that is 12, and so is that 12. And that takes care of the 4. All right, we are now ready to do some simplifying and write our overall reaction. Okay, so the electrons cancel. We have 12 on either side. They're out. All right, so as I go, I'm just going to start up here. Here I have 15 hydrogen ions on the left side, but down here I have 12 hydrogen ions on the right side. So we're going to simplify that just like we did when we were doing Hess's law, same thing. So those 12 are out entirely, and this becomes 3. So I can bring that down 3 hydrogen ions. Next is 3 ClO3s, -1. And then down here, I'm going to need to remember we've got some stuff on the left down here. So here I have 12 waters on the left. Up here, I have 6 waters on the right. Again, we can reduce that down, simplify, subtract 6 waters from both sides. Those disappear entirely. This becomes 6. So now we have 6H2O liquid. And then our last substance on the left is 4AS solid. Now we do the right side. We have 3HClOAQ. That takes care of that. We have 4H3ASO3AQ. That takes care of that. Everything else is canceled. So I think we got it. But I'm going to double check it, as you should also. So let's check. 3 hydrogens there and another 12 there is 15. 3 hydrogens there and another 12 there is 15. Hydrogen's good. 3 chlorines there, 3 chlorines there. 3 times 3, 9 O's, and another 6 there is 15. Here we have 3 O's there, and another 12 is 15. O's are good. We already did hydrogen. We already did O. 4As here, 4As here. Balanced. Let's check the charge. Here we have 3 plus 1s, which is plus 3. Here we have 3 negative 1s, which is negative 3. Neutral, neutral. Total charge on the left, 0. Neutral, neutral. Total charge on the right, 0. So this equation is balanced, both atom or ion-wise and charge-wise. I wanted to show you this one because this kind of incorporates all of the possible things that can be done in balancing a redox reaction in acidic solution. So, having done that, hopefully that made it a little clearer for you. And now we will go back and begin today's lesson, which is very, very similar. Let me close that. Now we're back to our notes. I'll scroll up, and there we are now to today's lesson, balancing a redox reaction in basic solution. If a redox reaction occurs in basic solution, then the equation must be completed by using hydroxide ions in water rather than hydrogen ions in water. So remember, in a basic solution, we have a predominance of hydroxide ions rather than hydrogen ions. Although remember, overall, we have both because water always slightly ionizes. First, balance the half reaction initially as if it occurred in acidic solution. So we are going to do exactly the same thing as we did if we were balancing this thing in acidic solution. Same steps, same order, exactly the same. Once we do that, we will neutralize the hydrogen ions on one side of the reaction by adding an equal number of hydroxide ions to both sides of the equation. What that then will have happen is the hydroxide ions that are added to the side that have hydrogen ions, when you add those two together, you end up making water molecules. And then we will simplify the reaction as before. So it's essentially the same thing with one additional step at the end. So let's go to this next example. And let's do this one. Excuse me. So we're going to complete and balance the following equation in basic solution. All right, first things first. We're going to do oxidation numbers so that we can determine our oxidation and reduction half reactions. So here's our equation. Again, it's net ionic already. And so I wanted to do this one because this brings up an interesting rule that we talked about when doing oxidation numbers, but perhaps you've forgotten. So here we have the cyanide ion, all right? There's no metal in there. They're both nonmetals, all right? Well, the overall charge on the cyanide ion, as you should know, is -1, which means the oxidation numbers of both of those cannot be negative, all right? And they aren't. So here's how do you determine which one has a negative oxidation number? It's whichever one is more electronegative. Hopefully you remember that when we studied oxidation numbers, but if not, this is a good review for that. Nitrogen is to the right of carbon, which means it's more electronegative. Of course, you could look it up too. That means it is going to have the negative oxidation number. And nitrogen, being in group 5A, then is going to be -3. All right. So what will carbon be? Well, if the overall charge on the ion is -1, then the oxidation number of carbon in this ion has to be +2. Okay, +2 and -3 yields -1. So here's the permanganate ion, MnO4 -1. Of course, O is -2, as it almost always is. There's 4 of those. With the charge on the permanganate ion being -1, then the oxidation number of manganese would have to be +7. Okay. So this is the cyanate ion. We didn't have to learn this one, but again, it's an ion. It's not all that common. The same rules are going to apply here. All right. Of these are all three nonmetals. Well, oxygen, of course, takes precedence. It's more electronegative by far than the other two. So oxygen, as it almost always is going to be -2 in this one. Now, we're left with two nonmetals yet. Well, here again, the electronegative rule comes into play. Nitrogen is more electronegative than carbon, so between those two, it is going to be negative. So again, based on nitrogen's location in the periodic table, that means it is still -3, which then now means carbon has to be what? Well, if the overall charge on the cyanate ion is -1, and these add up to -5, that would then mean carbon in this particular ion has an oxidation number of +4. MnO2, O of course is -2, two of those, which makes the manganese +4. So there are oxidation numbers. So if we make a quick analysis there, carbon went from +2 to +4, which is oxidized. Nitrogen is -3 all the way through. Oxygen is -2 all the way through. Manganese then ends up getting reduced, going from +7 to +4. So now we could be able to set up our reduction and oxidation half reactions. So if manganese got reduced, then the substances that contain manganese will be involved in the reduction half reaction, which would be MnO4 -1 AQ going to MnO2 solid. With carbon being oxidized, the substances that contain carbon will be in our oxidation half reaction, which would be Cn -1 AQ on the left and CnO -1 AQ on the right. So there are our two half reactions. So we're going to balance these half reactions as if they were being balanced in acidic solution. I know it's not, but we start off as if they were. All right. So first things first, balance everything other than H or O. Here that would be Mn, it's balanced. Here that would be C and N. They are both balanced. Nothing needs to be done there. Secondly, balance O with water. Here we have 4 O's here and only 2 here. So we're going to have to add 2 H2O's to the right side to bring our O's in balance. Here we have an O here and none on the left. So we would need 1 H2O on the left side there to balance that. Next is we balance hydrogen with hydrogen ions. So no hydrogens here, and we have a total of 4 here. So we're going to need 4 hydrogen ions. AQ, of course, on the left. No hydrogens here, none here. We have 2 here, so we're going to need 2 hydrogen ions on the right. Lastly, we balance charge with electrons. So the side that is more positive, we're going to add electrons to. So here we have 4 plus 1s, which is +4. The overall charge on the permanganate ion is -1. So we have a total charge on the left of +3. Everything over here is neutral. So we're going to have to add 3 electrons to the left side to make the charge balance. And again, you should always be thinking about this. In a reduction half reaction, electrons are gained. They must appear on the left side of the reaction. The bottom one. So water is neutral. The charge on the cyanide ion is -1, so our overall charge is -1. Here the overall charge on the cyanate ion is -1. Plus we have two hydrogen ions, which are both +1. So we have a -1 and a +2, which is a +1. All right, so we add electrons to the more positive side, which is the right side. What's the difference between -1 and +1? Well, that difference is 2. And so we're going to add 2 electrons to the right side. -2 and +1 equals -1. So we have done that. Now, next, the electron transfer must be equal, right? Here it is not. So we need to multiply one or both half reactions by an integer so that they are equal. Well, we're going to have to multiply both of them. The top one by 2, the bottom one by 3. So let me distribute those. So that becomes 6, that becomes 8, 2, 2, 4. And that takes care of that. Bottom one, 3 waters, 3 cyanides, 3 cyanates, 6 hydrogen, 6 electrons, and that takes care of that. All right, so we're going to simplify, reduce, and bring our reaction down, bring it back together as one whole reaction, and then we will finish it up. So I'll start here. The electrons, of course, cancel. They have to. The electron transfer must be equal. Here we have 8 hydrogen ions, and here we have 6 on the right. The 6 are gone, which gives us 2 hydrogen ions on the left. We have 2 permanganate ions. Down here we have 3 waters. All right. Over here we have 4 waters, which means we're going to have a water over on the right side. So those are out completely. And this 4, of course, then becomes 1. Then we have 3 cyanides left on the left. Go to the right side. So I'll start up here. We already have a water. We've taken care of that. So we have 2 MnO2 solid. The water we've already done. We have 3 CNO-1. And we've already taken care of the hydrogen ions and the electrons. So here's where we're at so far. If we had balanced this reaction in acidic solution, we would be finished. However, this is done now in basic solution, so we have an additional step to do. And that step is this. We neutralize, as in the instructions, we neutralize hydrogen ions with hydroxide ions. All right. We're going to add those to both sides of the equation. Both sides. So here is our hydrogen ions. They're here. They could be over there, but here in this reaction, they're on the left side. We have 2 hydrogen ions. We're going to neutralize by adding the same number of hydroxide ions. So we're going to add 2 hydroxide ions here and 2 hydroxide ions to the other side. We're keeping everything in balance, right? Both atoms, ions, and charge by adding hydroxide ions to both sides of the equation, all right? Now we're going to do some simplifying again. When you add 2 hydroxide ions and 2 hydrogen ions together, you get 2 H2Os. So that becomes 2 H2Os, all right? We have one last thing to do because now we have 2 H2Os on the left. We still have an H2O on the right. We can reduce. That one is going to go away, and that is going to become 1. So now, I'm running out of room. Sorry about that. I wrote too big. bottom line is now we can finish this thing off. There we go. So what are we left with? We have an H2O on the left, only one. We still have our 2MnO4 minus 1 AQ. We still have our 3 cyanide minus 1 AQ. On the right, that H2O has been canceled. It's out. We have 2MnO2 solid. We have 3 CNO minus 1 AQ. And now we have 2 hydroxide ions. This shows us that we have balanced this reaction in basic solution. Basic. Before we move on, we need to double check and make sure we are in balance, both charge-wise and atom or ion-wise. So let's do that. So here we have 2 H's, and here we have 2 H's. Done. 1 O and 4, let's see, 8 O's there, and 1 there is 9. Here we have 4, and 3 is 7, and 2 is 9. The O's balance. 2 Mn's, 2 Mn's. Done. 3 C's, 3 C's. Done. 3 N's, 3 N's. Done. So all the atoms / ions are balanced. Let's check the charge. Neutral. 2 negative 1s is -2. 3 negative 1s is -5. Our total charge on the left side of the equation is -5. On the right, neutral, 3 negative 1s and 2 negative 1s, -5. -5 on the left, -5 on the right. Done. All right. So, in closing, when you balance a reaction, a redox reaction in basic solution, we do the exact same things in the exact same order as if we were balancing it in acidic solution. Do that first. Once we do that, we're going to neutralize our hydrogen ions with hydroxide ions. You will add hydroxide ions to both sides of the equation. All right. These then, the hydrogens and the hydroxides become water. Check and see if you can then reduce water from either side. You probably will. And then rewrite your equation. Check it for balancing both charge and atoms and ions, and you should have it. All right. So on the assignment for today, not only is there, excuse me, several reactions for you to balance there in basic solution, but on the back of that assignment, there is also some fill in the blank on the next section. So what I wanted you to do is, as you do that assignment, read ahead in your notes to the next section, which is, as you can see right here, is voltaic cells, because that's going to be the focus of our study for the next several days, actually. So I want you to read through that, answer the questions from the notes, give you a basic idea what a voltaic cell is. And then over the course of the next several days, as I said, we will go into much greater detail into how a voltaic cell is set up and what they do for us. All right. So this is Mr. Keister signing off for today. This was our lesson on balancing redox reactions in basic solution. I'll catch you next time. Everybody take care, stay safe, stay healthy, and hopefully I'll see you soon.